Hello, everyone, and thank you for joining me for another learning session in chemistry. If you are watching this video on the day it was assigned, go ahead and set up your focus notes. If you are watching this at any other time, I welcome you to our learning opportunity and thanks for joining us. The topic for today is colligative properties, and the essential question is how are the properties of vapor pressure and osmotic pressures and freezing and boiling points affected by dissolving a solute in a solvent? So the idea here is that you no longer just have a pure solvent, just one type of particles, but you have things mixed together. How does that change some of these things called colligative properties? Go ahead and pause the video if you need to continue to set up your focus notes. Otherwise, let's get into it. So the first thing I want to do is just define this idea of a colligative property. So a colligative property or property in general, remember, is like a chemistry describing word. So how do we describe things? Those are properties. So a colligative property is a solution property, and it depends on the concentration or the amount of solute particles rather than the actual identity of the solute particles. So in this picture here, these two things look very different. One is yellow, one is clear, one has lots of elements, one only has two different kinds of elements. But what matters is that they are both ionic solutions that are zero point 0.1 molarity. That is the key here. That's what makes it a colligative property. So if you remember back to the essential questions, colligative properties are things like vapor pressure, osmotic pressure, freezing point, boiling point changes. Those will all be the same for these two solutions. They will have the same vapor pressure, same osmotic pressure, same change of freezing point and boiling point because of the fact that they're both zero point 0.1 molarity and they both have ionic solutions, so ions floating around, and the same number of ions. And we'll talk about that a little later. So this is what makes it a colligative property, focusing on how many solute particles there are rather than just the identity. The first colligative property we're going to talk about is called vapor pressure lowering. So, spoiler alert, it already tells you there's going to be less vapor pressure. So, let's do a quick review of what vapor pressure means. So, a vapor pressure means anytime you have a liquid sample, it doesn't have to be just pure water, anytime. It could be a cup of coffee sitting in front of you, a lake outside, a puddle, a glass of orange juice. Anytime there's liquid, there is at least some amount of particles. Usually think of things as like the top layer that are evaporating. They are collecting energy from the energy available, and they are turning into vapor particles. So solvent particles are evaporating, or the liquid particles are evaporating in some way. And that causes a little bit of pressure right here. Think of it. Usually the atmospheric pressure all the way around that liquid sample, it kind of pushes back against that vapor pressure, and we don't really notice anything happening. But in a solution, you don't have as much vapor pressure. Well, let's think about why that is. In a solution, you no longer have just one kind of particle attracting to itself, like water attracting to water, and then it can evaporate some as it gets some energy. But in an aqueous solution, the reason you have a solution is because there are particles that are attracting to each other. There's at least one type of solute and the solvent that are attracting, and they make that homogeneous mixture. Well, because of that, those solvent particles don't want to leave. They don't want to leave that solution because they're attracted to the solute. A silly analogy that might help is think of that if you had like a babysitter that brought a couple of kids to the park, and then there was a bunch of other kids to play with at the park, and then the babysitter's like, oh, time to go for us to go home, and the little kids are like, no, I don't want to go home, I want to stay and play with all of these new friends. Well, think of that, it's a little silly, but think of that as what's happening in a solution. The natural world is saying that the solvent should be evaporating, but the solvent is saying, no, I want to stay in this solution with all of my friends. There's an attraction there. They want to stay. So you're just naturally going to have less particles turning into vapor and evaporating and causing that vapor pressure. This means that if you're trying to boil a solution, which means you have to have enough vapor pressure to push through the atmospheric pressure, it's going to take more energy. And we're going to talk about that later. All right, vapor pressure lowering. That's our first colligative property. Go ahead and pause the video and just process what you've written or heard so far, a level 1 type COSTA question. All right, continuing on, our second colligative property is something called osmotic pressure. It is possible you've heard of osmosis. Maybe if you've taken a biology class and talked about like things that can go between cell walls, that's kind of like this idea of osmosis or the same idea. So when we talk about osmosis in this context, we're talking about the fact that a solvent can go through some type of membrane. That's what permeable means. It can go through membrane would be like some type of barrier, and it's only the solvent that can go through it. So, not the solute or any other particles from that solution. So, I'm going to show you a diagram. This is the original YouTube. Ha ha ha. This diagram is just representing some type of system. It could be cells, it could be some type of filter, something that was built where osmosis can happen. Here's the barrier, the membrane. And like it's showing you here, there's a certain number of particles of solute on both sides of that membrane. If you count them on this side, it's the same number of solute on that either side of that membrane. But look at what's happened here. The solvent was allowed to go through that membrane. So on this side, there's more solvent. Well, the reason we care about that in this unit on solutions is that you've now changed the concentration. This side, there's less solvent, same solute, so that concentration has increased. On this side, there's more solvent, same solute, so that concentration has decreased. That could be a problem depending on what this is, a filter or some type of cell setup where there's needs to be a certain amount of concentration either to provide enough nutrients or to protect from contamination. But this is important, the fact that the concentration changed. So, osmotic pressure is how much pressure do I need? Think of it kind of here in this space above the solution to prevent osmosis. So, I want there to be a pressure here pushing back against this solution so the solvent cannot move through it. Or imagine that how much pressure would I need here to push the solvent back through the membrane and let osmosis occur, or maybe the idea of reverse osmosis. So, osmotic pressure is kind of this idea where we're trying to keep osmosis from happening or force like reverse osmosis to get the concentrations back to however we need them to be, or maybe the way they started. So, osmotic pressure is something that we are going to quantitatively measure. And this is the equation for osmotic pressure. This symbol pi stands for osmotic pressure. So, don't try to plug in 3.14. I know pi is a very common symbol in math. In this context, it just means osmotic pressure. But it equals capital M, capital R, capital T. Now, this might kind of sound familiar. Pressure, molarity, RT kind of sounds like PV equals nRT. Maybe you remember this from our ideal gas laws. So, really, what we've done is we focused on the fact that this is solution, so molarity, and we know that molarity is moles over liters or moles over volume. Well, look at what we did here. We took the volume from this side, put it under moles, because remember from ideal gas law, this was moles over volume. So moles over volume is really the same as molarity. So V and N can drop out. And then we just have pressure or osmotic pressure on this side. And so you can see that this is another application of where moles come back. And since moles come back, guess what else comes back? Time for some mole jokes. All right. What do you get when you cross Avogadro and a sheet of music? You get a molody. And then, who is Avogadro's celebrity crush? Now, this is kind of an older person that you might not have heard of as well, but remember, Avogadro was old. His favorite celebrity crush is Cindy Crawford. She is his favorite supermodel, known for her very prevalent beauty mole. So that's what's going to make Avogadro crush on Cindy Crawford. Okay, back to our equation. So, just to make sure we know what all of these things stand for, pi is really osmotic pressure. So, again, don't try to plug in 3.14. It is the pressure of needing to prevent osmosis, right? Capital M is molarity. Remember, that's moles over liters of solution. And then R was a constant. Remember, established by this guy, did a bunch of experiments, and then figured out what number do we need to plug in to make this equation work. So the number is 0.0821, but this whole thing is the label. Don't forget to put that whole label on this number. Don't try to plug things into this box. This label goes with this number. And then capital T is temperature, but as you can see in the units of R, the temperature needs to be in Kelvin. Remember, that's nice for math equations, especially because then we don't ever have to deal with negative numbers because Kelvin can't go below absolute zero. And so that's one of the reasons we use Kelvin in our gas laws, especially. All right, well, let's see a practice example like this. So, my example that I chose is something that is going to feel like, oh, this is something that happens in our real world. Even if the people that do this don't necessarily think about osmotic pressure, that's really what's going on here. So, the situation I picked is curing meats, which is basically a way to preserve them. And the reason that it works is because you just basically take like a fresh meat sample and you pile lots and lots and lots of salt on it. And then what happens is that salt draws any water out of the natural microorganisms or bacteria that would be in the meat, and then they can't grow. So then this preserves the meat, it keeps it from spoiling and keeps it from being getting if you from getting sick if you eat that meat. This was really popular, really important back before freezers or refrigeration was very common in homes. So what people would do is they would take salt or make a salt solution, put the meat in there, and then they would put it maybe somewhere cooler, or they would even sometimes bury it in the ground where the pressure was higher, or put it like lower in their cellar, like in their home, and that would help preserve the meat. So now when people do this either in their homes or at like a butcher shop or a deli, what they'll do is they'll take about 20 grams of salt and just like table salt, sodium chloride, 100 milliliters of solution. So they'll put some water in that, a little bit higher than room temperature to get that all to dissolve. And then they usually vacuum seal it. That vacuum seal kind of builds up a whole bunch of pressure. And then that pressure is really osmotic pressure that keeps the water that's naturally in the solution or naturally in the meat from going back into that bacteria. So that pressure is preventing osmosis. So again, this is a real thing that would happen in our world, though sometimes the people that are doing this curing of meats, they might not be thinking about this equation, but we can think about this equation and use this example to practice calculating osmotic pressure. So we're looking for osmotic pressure. We need the molarity, we need R, and we need T. So let's try this out. So osmotic pressure is what we're looking for. That is pi. So what I need is capital M. And capital M by definition is moles of solute and liters of solution. Well, I don't give you moles of solute, but I tell you there's 20 grams of salt, which is table salt, sodium chloride. So I have 20 grams of sodium chloride. I look at the periodic table. I add up the mass of one sodium and one chlorine. That's where this 58.44 comes from. By definition, that's the number of grams in 1 mole, but I put grams on the bottom so that grams will cancel. I'm left with moles, and I'm not worried about sig figs yet, so I get this number, 0.34223 moles of solute. But I need molarity, so I need to divide it by my liters. Well, again, I don't give you liters, but I give you 100 milliliters, so I can do a metric conversion. I need milliliters on the bottom to cancel it, so I'm taking 100 divided by 1,000 and zero point 0.1. And this is just a metric conversion, so really this is 0.10000, not worried about sig figs yet again, because this is just a definition of the conversion between milliliters and liters. But then now I need molarity. So I take my moles of solute divided by liters of solution, and I get 3.4 molarity. A pretty high concentration of salt, but that's needed to draw all of that water out of the bacteria cells and keep it from growing. So that's my molarity. Now I need R. R by is just a constant. So even though it's not given in the problem, you always have R. It's 0.0821 liter atmosphere over mole Kelvin. So again, this is the label that goes on this number. And then I need my temperature. But remember, your temperature has to be in Kelvin. If you forgot about that, you would notice it when you do the problem because you can see that there's Kelvin in the units for R. So to get to Kelvin, you take your Celsius temperature plus 273. So I get 301 Kelvin. So to set up my equation, it's osmotic pressure equals molarity times R times temperature. So you can see that K over K cancels. Molarity is the same as moles over liters, so liters over moles cancels that. And then we're left with ATM, which is what we're looking for. When you do your math equation, so first just type it in your calculator, multiply all three numbers, go ahead and pause the video and get your answer on your calculator. When you get the answer on your calculator, you get something like 84.0211 or something like that. But we can only keep 2 sig figs based on our data that we started with. So our final answer will be 84 atm. And atm is a unit of pressure. And so this tells us that's how much pressure needs to be in that vacuum seal to prevent osmosis naturally occurring. And this is a pretty high amount. If you're sitting in just kind of a room on Earth right now, you're probably feeling around 1 atmospheres, maybe a little bit higher, lower, depending on your exact location. But this is definitely a very high pressure, again, to prevent osmosis happening in that meat sample. All right, osmotic pressure. Go ahead and pause the video, process a little bit what you've seen so far, and write a level 2 COSTA question. Active learning, don't skip this step. All right. The next two colligative properties we're going to talk about are both about phase changes. So the third one is boiling point elevation. So what does that mean? Anytime you have a solution, the boiling point will be higher than a pure solvent. So if you had something like water, which boils at 100 degrees, if you dissolve anything in that water, the solution boiling point is going to be higher than 100 degrees. All right, well, why is that? Well, remember, if you want to boil something, you have to break the forces or the intermolecular attractions between the particles, get enough energy so they can pull away and then turn into a gas. But when you have a solution, there's more intermolecular forces. You have attractions between the solute and the solvent, and also the solvent and the solvent. So, to get enough vapor pressure to break through the atmospheric pressure and start to actually boil, you need to add a lot more energy to break those different attractions. So then for freezing point depression, it's pretty similar, only it's the opposite. It's just a more extreme temperature, just like the boiling point is more extreme. So what this means is if you have anything dissolved together in a solution, the freezing point will be lower than a pure solvent. So again, thinking about water, water freezes at 0 degrees Celsius. So if you dissolve anything in that water, the freezing point will be lower than 0 degrees Celsius. Why is this happening? Well, in order to get something to freeze, you need to allow the particles to move slow enough and attract to each other and form a solid pattern and then kind of just vibrate in place. But because you have a solution, the solute and the solvent attraction keeps the solvent from attracting to other solvent particles. And so you need to remove more and more and more energy so that the solvent doesn't roll around and attract to the solute anymore, but instead it is able to attract to the solvent. And then it can form that pattern, that solid pattern of whatever type of molecule or ions that are present and actually freeze. So, this is, of course, why we put salt on our icy roads or sidewalks, especially here in Minnesota. What happens is when you put the salt on the ice, that even if it's not pure water, the ice has frozen, the water has connected to other water molecules and just kind of is vibrating in place. But once you put that salt on that ice, the water is more attracted to that solute, that ice or that salt, and so then it pulls away from its crystal structure of the ice and it's now attracted to the solute and then it is not frozen in place anymore. The particles now start to attract and move towards the solute. And so then it lowers the freezing point and it actually goes back to being liquid. And so then you don't have that ice anymore. Okay, so one way to just talk about these colligative properties is just qualitative, like the boiling point will be higher, the freezing point will be lower. But we are also able to calculate that change. So first we're going to talk about non-electrolytes. Remember, this means there's not electricity passing through it, so there's no ions dissolved in the solution. So this is the equation for calculating the boiling point elevation when you just have molecules dissolved in your solvent. So the change of temperature boiling equals a boiling constant. Every solvent has one. You can look it up, times molality. So then to figure out the boiling point of the solution, you take the boiling point of the pure solvent and you add that change of temperature that you just calculated here. So if your solvent was water, water boils at 100 degrees. Whatever you dissolved into that water would give you a molality. You'd find the K value for water, which would give you your change of temperature. You would add it to 100. That would give you the boiling point of the solution. All the same stuff for freezing, just replace B with F for freezing. So change of temperature freezing equals a freezing constant for every solvent and the molality. But then remember, freezing points are always lower than the pure solvent. So the freezing point of your solution is the freezing point of the pure solvent minus that change of temperature freezing you just calculated. So again, if we're using water, 0 degrees is the freezing point of pure water, to 0 degrees Celsius. You would take the Kf value for water, the molality of your solution that you made, that would get you, multiply those, that would get you your delta TF. You would take 0 minus your change of temperature to get the freezing point of that new solution. So again, Kb and Kf are constants. Every solvent has one. You can just look them up or they'll be given. You could go ahead and write down the K values for water because we use them quite a bit. So what this means, the K values, it's degrees Celsius per molality. So when you look at this, it says for every molality that you have for water, the change of temperature would be 0.512. So if you had two molality solution, you would change your temperature about 1 degree. And if it was a higher molality, you get a higher change. And then same with your freezing, only the number is 1.86 degrees Celsius per molality for water. So if you have a 1 molality solution, your freezing temperature is going to be negative 1.86 because it goes down by 1.86 for every molality. So again, these are only specific to water. And then again, quick reminder, molality is moles of solute per kilogram of solvent. So this is how we calculate the actual number of how much did the boiling point raise, how much does the freezing point get lower if you have a non-electrolyte. But then I got one more set of equations for you. What if it is an electrolyte? So now you've got ions floating around in your solution, and that matters because that changes the number of particles that you either have to break attractions between or slow down in order to get your new temperature. So you'll notice that the two equations are very similar. It's still delta T, K, and M. But what changes is there's this little I. And the little I stands for how many ions are now floating around in your solution, which changes the colligative properties because it changes your concentration of solute particles. And so again, you have one for boiling and one for freezing. All of that means the same, but then now you have to figure out the number of ions, which will multiply and change your change of temperature. A little side note for those of you that read a lot about chemistry or take a higher level chemistry class, you might hear that the little I is sometimes referred to as the Van 't Hoff factor. I don't generally use that term in pre-AP chemistry or accelerated chemistry, but if you hear it, you'll know what that means. Really, it's making you think about how many ions are present in a solution or a sample. Let's just practice that really quick. How do we identify the number of ions? So if you have something like aluminum chloride, the number of ions is not just the number of atoms, it's how many positive pieces and how many negative pieces there are. Well, in this case, aluminum is positive and there's only one, and chlorine is negative and there's three because of this little three. So that's really 4 ions, 1 positive and 3 negatives. But if you have something with a polyatomic ion, remember that this is one group, and you would find it on a reference sheet somewhere if you didn't remember that. It's called sulfate. So you have 1 sulfate, which is your negative ion, and then 2 sodiums, which are your positive ions. So total, you have 3 ions. So again, it's the number of ions, not just the number of atoms. So sulfate stays as 1 negative ion, and then you have 2 sodiums. That's where the 3 comes from. And again, the reason we have to figure this out is because colligative properties are based on the number of solute particles. So if there's more solute particles, then you have more particles that you either need to slow down or speed up or break attractions, which will give you a more extreme change in temperature, either a higher change for boiling or a lower change for your freezing. So a bigger change, more extreme. Okay, so now that we've seen some calculations related to boiling point and freezing point, what could we do with this? Well, there's actually a pretty cool um, unknown determination thing we can figure out looking at the change of either boiling point or freezing point. We can determine the molar mass. So imagine with me, if you want, we can make it kind of extreme. Imagine you're a crime scene investigator and you go to the scene of the crime and you're examining the victim and you notice that underneath their fingernails there's some chemical. And so you want to know what that chemical is because maybe it will give us an idea of what happened to the victim, or maybe it will give us an idea of a location of where they maybe were injured or something about the crime. So you take 5 grams of that unknown, we'll call it X, and you dissolve it in water, and you know that it's not conducting electricity. So it's not electrolyte. So we're not going to have to worry about the little I in the equation. But now the solution freezes at -1. You knew it was going to change temperature because it's not pure water because you dissolved that X into the water. And now it froze at -1. We can use that change of temperature and this data to determine the molar mass. And then once we know the molar mass, we can use databases and the physical description of that sample that we found to identify it. Remember, molar mass by definition is the number of grams of a compound or of a substance in 1 mole of a substance. So I already have my grams of my substance, but what I don't know is moles. But remember, we just learned that changing the temperature for freezing is related to molality. Molality has moles in it. So that's what we're going to use. So there's really 4 steps to solve. As long as you have this data, here's the 4 steps you'll always use. Start by finding the change of temperature. We know that water freezes at 0 degrees, and you've changed the temperature. Now it freezes at -1. So the change of temperature is 1 degree Celsius. The second step is you can plug that 1 degree Celsius into change of temperature equals Kf times m. And little m is molality. So I can say 1 degree Celsius equals 1.86 degrees Celsius per molality, and I can solve for my question mark little m. This is the Kf for water because water is my solvent, and that is a constant that you can look up, or it was given to you in your notes in this video. But now I do a little bit of algebra. I take 1 degree Celsius divided by 1.86 degrees Celsius per molality. Degrees Celsius will cancel, and then molality will equal 0.5376, whatever. Don't do the sig figs yet. You can just leave this number actually in your calculator. But this is the number of moles per 1 kilogram or 1,000 grams. I don't have 1,000 grams. I only have 60 grams. So I can't call this my number of moles for my molar mass. I have to find how many moles of X are in 60 grams of water. Well, I'm going to start with my 60 grams, and I got to get rid of grams and get to kilograms. So I use the metric conversion, 1,000 grams for every 1 kilogram. I put the grams on the bottom so that the grams cancels. I'm at kilograms. So now I can use molality and say 0.5376 moles of solute equals 1 kilogram of water. That comes from just the definition of molality, water, because that's what my solvent was in this example. Kilograms of water goes away. I'm at moles of solute, which is what I was looking for. So I take 60 times my 0.5376 divided by 1,000, and I get 0.0322. Again, not worried about sig figs. This is just a math number for now, but it's moles, and it's moles of X. So now I can determine my molar mass of X. Remember, the definition of molar mass is how many grams of a substance per mole of a substance. So I have grams given to me, and moles is what I just figured out by using molality from my change of temperature that I calculated from lab. So 5 grams of X was the given. 0.032258. I got that from molality. 5 divided by this. When you do the math answer, you get like 155.00 something something. But I can keep 3 sig figs based on all the numbers in my data, so it will round to 155 grams per mole. So then again, what I would do with this number is I would maybe type it in a database, or I would look up what compounds or elements would have this molar mass. But then I also know what the compound looks like. So between the physical description and the molar mass, I'd be able to either narrow it down or completely identify this unknown. And that could help me solve the problem that I was trying to solve, whether it was the crime scene investigator or something else. So this is an application of using the actual change of temperature to do something useful for a chemist. All right, go ahead and process what you just saw or what you heard by doing a level 3 question. Go back and rewatch anything as needed. But when you're done with that level 3 question, pause the video if you need to. Here's some things you could do to finish off your learning for today. Finish any COSTA questions. You could write your summary that goes back and answers the essential question from today. I have a couple example problems that you could practice just to see if you understood it. So you calculate the new boiling point of these solutions. And then again, paying attention to the fact that the solvent was ethanol. So you need a new K value and a new boiling temperature. And then this one is water. Water, the K value you have in your notes, or it was 0.512 degrees Celsius per molality, and water usually boils at 100 degrees. So this would be a way to calculate, just practice what you did today. Do any practice assignments either from me or from any other teacher if you're watching this for a different class, or ask questions. So again, you could, if you're watching this with Miss Killinan's class, you could come to class soon and ask questions, or send a message if you had questions, or talk to whatever teacher you have access to get your questions answered. Thanks so much for listening today and joining me in learning. We'll talk to you next time.